Hello everyone, my name is Simon and I'll present the paper Mechanized Verification of a Fine-Grained Concurrent Queue from Meta's Folly library. First, I'll say a little bit about the queue that we verify in this paper. It's called the MPMC queue, and it's first of all a very efficient and practical queue. It was originally developed by Nathan Brunson at Meta, where it's used in production, and where Meta has found that it scales extremely well to thousands of consumer threads and hundreds of thousands of producer threads. A C++ implementation of the queue is included in Meta's open source library Folly, which can be found on GitHub. So all in all, this is a really interesting and intricate data structure that is used extensively in practice, but it has not been formally verified or studied at all. And that is where we come in. In this paper, we prove that an implementation of the queue in an ML-like language with concurrency support is a contextual refinement of a simple log-based queue. Roughly, this just means that the queue works and that it's linearizable. A little bit more precisely, it means that from the point of view of a client that uses the queue, the MPMC queue, which looks like this, is completely indistinguishable from this extremely simple coarse-grained log-based queue. So we take this very simple queue to be the specification of what it means to be a concurrent queue, and then we prove that the MPMC queue behaves accordingly to this specification. We prove this refinement using the iris-based logic relloc, which is a logic for showing these types of contextual refinements. Now, as depicted here, the MPMC queue is implemented using something called a single element queue, which in turn is implemented using something called a turn sequencer. So to verify the MPMC queue, we also had to verify these two submodules. Finally, during our verification, it turned out that the MPMC queue has what is called an external linearization point, and that relloc isn't able to verify data structures with external linearization points. Therefore, in order to verify the queue, we had to extend relloc with additional capabilities that makes it possible to handle external linearization points. And these extensions are general. And in the paper, we give a proof pattern that applies to all data structures with external linearization points. Everything is fully formalized in COC, and the extensions to relloc has been upstreamed such that they're available to all relloc users. I will now explain some of the key ideas behind the MPMC queue and give a high-level overview of the verification. So a key goal in the design of the queue was to reduce contention by, instead of having one queue, having an array of queues. So here in this diagram, every box is a specific type of subqueue called a single element queue. Now, in order to enqueue and dequeue an element to the queue as a whole, one must enqueue or dequeue the element to one of these subqueues. To manage this, we have two ticket dispensers which are maintained alongside this array. And these are just references to an integer. Now, enqueuing an element x to the queue works as follows. First, a ticket is taken from the enqueue ticket dispenser, and this is done by atomically incrementing it with fetch and add. This gives some ticket t, and by modding this number with q, we get an index to some single element queue in the array. The value x should now be enqueued to this single element queue. So we call the single element queue's enqueue operation on this subqueue, and we give it the value x. Now, in addition to this, enqueueSec also takes a number, which we call a turn, which specifies the order in which the value should be enqueued to this queue. And in our case, this is just the number of times that we've wrapped around the entire queue, which is t divided by q rounded down. And giving the turn in this way ensures that the ticket we took from enqueue ticket in the beginning also determines the order in which we get to enqueue our element to the single element queue. And this concludes enqueue, and dequeue works in a very symmetric way. And this design with Q sub-Qs ensures that up to Q, NQ, or DQ operations can proceed sort of completely independently of each other, the only point of contention being the ticket dispenser. And this is a big part of what makes the queue so scalable, but it also makes the verification more challenging. Let's return to this picture again. As we've just seen, the MPMC queue is implemented using the single element queue. And as I mentioned before, the single element queue is implemented using the turn sequencer. So, of course, to verify the MPMC queue, we also had to verify these submodules. I won't explain them in great depth, but the turn sequencer is a form of concurrency primitive similar to, but not the same as a lock. To see how it works, consider this example with 3 threads that use a turn sequencer. The 3 threads call wait, which is similar to acquire on a lock, and then in the end they call complete, which is similar to release on a lock. Similar to a lock, the turn sequencer here ensures mutual exclusion, that these 3 critical sections won't execute at the same time. But in addition to what a lock guarantees, it also ensures that the critical sections are executed in the order as given by this turn argument to wait. So here we are ensured that this critical section will run first, then this critical section, and finally this critical section. So we can say that a turn sequencer ensures a form of ordered mutual exclusion. The specification that we show for the turn sequencer looks like this. It's very similar to the type of specification that you would give for a lock, but with 2 key differences. First of all, the resource protected by the lock is slightly different to expose this fact that the turn sequencer executes critical sections in order. And then there is a resource of turns that's used to manage how the turns are used with the turn sequencer. This specification is then used to verify the single element queue, which uses the turn sequencer to ensure that its DQ and NQ operations are carried out in the correct order. The specification that we give for the single element queue looks like this. Again, this one is very similar to a typical kind of specification that you would give for a queue, and it's called a per element specification. And again, there are 2 key differences. One of them to expose the fact that DQ and NQ are carried out according to the turn arguments, and then some resources to manage how the turns are used with the turn sequencer. This specification is then used to verify the refinement result for the entire MPMC queue. And I don't have time to go into any details of this proof, but let's just take a quick glance at the invariant that we use. The invariant is sort of the most important and intricate part of such a refinement proof. And this invariant contains a lot of moving parts to make everything work. It contains some very standard things. For instance, there are some points to predicates to represent the physical state of the queue. There are some assertions to make sure that the MPMC queue and the coarse grain queue have the same state. And then since the physical state of the MPMC queue doesn't necessarily correspond to the abstract state of the MPMC queue, we use a ghost list which keeps track of the elements in the queue. Then we have some invariants for all the single element queues in the array. And for these single element queues, we need to keep track of all of their turns and so on. Then we also have this part, which is for handling the external linearization point in DQ. So DQ doesn't always have an external linearization point. It also sometimes has a fixed linearization point. So this stuff here needs to handle both the case where DQ has a fixed linearization point and the case where DQ has an external linearization point. And when the linearization point is external, it sort of needs to interact with the corresponding DQ operation that carries out the external linearization point. And in here, precisely here, we make use of our extension to relic, which is what I'll cover next. When proving contextual refinement of a concurrent data structure, one needs to prove refinements for each operation on the data structure. For instance, to prove refinement of the npm-c queue, we need to prove that its dequeue operation refines the coarse-grained queue's dequeue operation. And in relic, the way that this is done can be summarized as follows. We first symbolically execute the implementation up to its linearization points, and this is why linearization points are very important when proving refinement. The linearization point is the execution step where the implementation changes its abstract state. So the specification must also change its state accordingly at this step. Hence, we symbolically execute the specification to completion. And finally, as the last step, one symbolically executes the implementation to completion. Now, when we began verifying the npm-c queue, we realized that its dequeue operation sometimes has what is called an external linearization point. An external linearization point is when the linearization point of one operation happens during the execution of another operation. For the npm-c queue in particular, when dequeue is called on an empty queue, its linearization point happens during the execution of the next enqueue operation. So for an external linearization point, this pattern doesn't work. The first step fails as we can't execute the implementation up to its linearization point, since the linearization point doesn't happen during its execution. And furthermore, due to the way in which relic's refinement judgment tightly couples together the state of the implementation and the state of the specification, there isn't anything else we can do either. So to remedy this, we sort of tweak relic to make it possible to decouple or split the implementation and the specification from each other. So we first generalize the normal refinement judgment such that the specification may be absent. So instead of this argument here being an expression, it's now an option of an expression. And when the specification is absent, we write the refinement judgment like this and call it a left refinement. We also add a new judgment that contains only the state of the specification, which looks like this, and which we call a right refinement. Relic's existing tactics for symbolically executing the implementation still works when the specification is absent, and we add new tactics for symbolically executing a right refinement. To split a normal refinement judgment, we add a new rule, well split. And crucially, when applying this rule, one gets the right refinement as a resource that one can then move around, for instance, put inside an invariant, which is crucial. Symmetrically to the well split rule, we also have a rule well combine, which is for combining a right refinement and a left refinement again. With these changes in place, one can then verify an operation with an external linearization point as follows. First, symbolically execute the implementation up to the point after which the linearization point may happen during another operation. Then apply well split to split the refinement judgment and get a right refinement as a resource that we can then put inside an invariant in order to transfer it to the other operation where the external linearization point happens. Then in the proof of the other operation, step forward the specification at the external linearization point and put the sort of evaluated specification back into the invariant. Then in the original operation, step forward the specification up to a point where it can be concluded that the linearization point must now certainly have happened in the other operation. At this point, one can extract the specification again from the invariant, and lastly, combine the two parts with the well combine rule and step the implementation to completion. In the paper, we explain this in more detail and show how this pattern is used for the npm-c queue. And this concludes the talk. Thank you for your attention.